Welcome everyone to the webinar on hazardous effects of a burgeoning space industry on the environment. Today we are joined by Eloise Marais, who is an Associate Professor of Physical Geography at University College London. There she leads a research group that seeks to determine the influence of humans on the chemical composition of the atmosphere, air quality, public health and climate. Today's webinar will explore the growing space sector and will look at the potential environmental harm of rocket launches and space debris on the atmosphere now and in the future. As always, there'll be a chance to ask questions at the end of the presentation, so please ask these in the Q&A option at the bottom of your screen at any point during the presentation. I will ask these on your behalf later on. Thank you for logging in today, and I'll just hand over to Eloise.
Super, thank you very much. I'm very excited to be participating in this webinar series, especially at a time where the UK is anticipating their first rocket launch, which should be sometime this month, although it has been substantially delayed. And so at this time where not only the UK, but many other parts of the world are starting to develop their ability to contribute to this new space race, we really should be starting to consider what the impact might be on the environment. So to just set the stage, to give some historical perspective, the space sector has really evolved over time. We've gone from just two nations dominating the space race, so Russia, the former USSR, and the USA, to a much more diverse collection of countries contributing. And you can see that reflected in this time series here, showing how the number of rocket launches per year has evolved to include China, private sector, again, NASA is still involved, India, Japan, Kazakhstan, and the EU, although their launch site is not located in mainland Europe. And so as a result, rockets are being launched from many locations in the world. There's a diverse mix of propellants that are being used. And so there really is this change in the kinds of impacts that it can have on the environment over time. I mentioned that the UK is anticipating their first launch from Cornwall. It's gone from having no spaceports to anticipated 7 spaceports. Most of these are in Scotland. And they'll be somewhat unusual in that there'll be a mix of traditional vertical rocket launches, and then also these air launches. So the first example we'll see of this will be from Cornwall. It's a Virgin Galactic flight, so it's an aircraft that reaches about 12 to 15 kilometers altitude and then releases a rocket, which then goes to orbit and releases the payload, which might include things like small satellites. And the anticipation in speaking to people from the media is that it's likely that there'll be 30 launches each year from the UK. And I think, if I'm remembering correctly, Virgin Galactic in the next few years is anticipating about 6 or 7 launches. But of course, these numbers evolve. An example of that is that the Cornwall launch was supposed to be, I think, in September, and it's been delayed due to a number of regulatory steps that need to be taken. None of those, unfortunately, are related to the impacts on the environment in the upper atmospheres, but it is substantially delayed, and we're sort of seeing that maybe this launch won't even take place in November, pushing it further back to December perhaps. And of course there's another launch site in Wales. Not only are new countries becoming involved in the space sector, but there's also this advent of a space tourism industry. But this has become a little bit quiet in 2022 as well. We saw 3 demonstration missions taking place in 2021. So these were from Virgin Galactic, from SpaceX, and from Blue Origin, all taking place in the US. But there's been a few additional very PR-centered launches by Blue Origin, and there hasn't been much since. So it's remained somewhat of a nascent industry for now, but there are, of course, rumblings of other countries developing their own capacity to have space tourism. And then rockets are getting bigger and they're starting to burn more fuel. And we had an example of that very, very recently. So the 16th of November, NASA launched the largest ever booster into space. So the booster is typically the portion of the series of rockets that burns first. So it's really having to work really hard to counteract the forces of gravity so that the rocket can go to about 80 kilometers altitude before then igniting the second stage and third stage rockets to eventually take the payload to orbit. And so this is called the NASA Space Launch System, and it has a propellant mass that's about 3 times larger than the propellant mass of a rocket that we have looked at in our research, India Space Research Organization rocket. So growing substantially. It's not just NASA that has these larger rockets, but SpaceX as well that's exploring having particularly large rockets that burn more propellant. And the consequence is that there's more pollution produced, as I'll show in the next few slides. There's also more payloads being launched into space. So SpaceX and many other companies have these mega constellation programs. SpaceX's Starlink has already occurred. There's been a number of launches that have taken up to 60 satellites into space in one launch. These are launched from the Falcon 9 rocket, which is about 26 tons. And there have been almost 4,000 of these satellites launched to date. And even though satellites are supposed to stay in low Earth orbit for about 3 to 5 years, we've seen 318 of these already deorbited. Then there's the Starship program, which is considerably more ambitious than Starlink. It's going to be using what's called the Raptor rocket, which is an order of magnitude heavier than the Falcon rocket. And the ambition from our Twitter overlord, Elon Musk, is that it's going to have about 3 launches per day, completely escalating the number of launches that take place typically in a year, and there's anticipated that there'll be about 30,000 satellites launched into space using this Pez dispenser style approach of releasing them into orbit. And then we can see this reflected in a recent record showing this dramatic increase in the number of objects in space. So the European Space Agency is very diligent about collecting annual surveys of the space environment, so the amount of activity that's taking place, and there's a lot of detail that goes into this report. In this particular figure that I'm showing from that report, you can see the number of objects that are being launched each year is fewer than 200 up until about 2016, 2017, and then that ramps up substantially as a result of these mega constellations to more than 1,700 by 2021. And you can also see how these are distributed by their kinds of purposes, and the majority are associated with communication. For science purposes, there's a slightly smaller contribution, which is a little bit of a relief for me. I make use of satellite observations to inform other research that I do to understand the impacts of humans on the environment. And so these play a crucial role in the research that I do. But of course, there is this issue of the potential influence that these could have on the environment. And so we're seeing increasingly cluttered skies. This is of particular concern for astronomers, but there's also an atmospheric impact impacting the chemical composition of the atmosphere. So this includes things like discarded rocket parts, spent satellites, and other kinds of junk that's accumulating in orbit. And unfortunately, the only viable disposal method that we have is complete burnup of these when these re-enter the Earth's atmosphere. And so just to go through some of the aspects that we focused on in our research leading to the results that we have obtained. So there's a range of air pollutants that are emitted from rocket launches, probably more than we're representing in the research that we're doing, but we made sure that we accounted for the majority of these. And it really depends on the kind of propellant that's being burned by these rockets. And there are 4 main propellants. And here I'm just showing examples from just a range of rockets that are routinely launched into space. So there's solid rockets, there's hypergolic fueled rockets, there's kerosene, which is used by SpaceX, and then there's cryogenic rockets, which we've seen for Blue Origin for their space tourism offerings. There's also liquid methane, which is starting to be explored as an option. I haven't included it here because we focused our research on 2019 before we had seen any demonstrations of liquid methane being used as a fuel. And so I've listed a bunch of chemicals here, and I don't want to inundate you with chemistry, but I do just want to point out the influence that these different chemicals have on the atmosphere. So before I do, the symbols here are NOx is nitrogen oxides, HCl and Cl or chlorine compounds, Al2O3 is alumina, it's a particle. Water vapor, unfortunately, is a pollutant when we release it into upper layers of the atmosphere because it is mostly foreign to those layers. And then black carbon or BC are soot particles. So it's the gases are NOx, the chlorine compounds and water vapor, and then the aerosols are alumina and black carbon. The two that I've highlighted here are the main ones that are really influencing the atmosphere. And I'll go through details of how we identify that's the case. There's some distinctions in the mix of pollutants that are produced from these different propellants. Cryogenic doesn't include any carbon. It's liquid hydrogen and oxygen, and so it doesn't produce black carbon, but it does produce nitrogen oxides and water vapor. And then all of the carbon-based fuels, which is kerosene, hypergolic, and solid, are all going to produce black carbon. They're also going to produce water vapor because there's hydrogen in the fuel, and nitrogen oxides, which come from the actual high temperature processes that take place during the launch. This is converting nitrogen in the air, which represents 79% of our atmosphere, from this non-reactive nitrogen into very reactive nitrogen. And then the solid rocket motors include additional pollutants, so the chlorine compounds and alumina. Black carbon is really the big ticket item in its influence on the environment from rocket launches. And so I just wanted to spend a little bit of time focusing on this. So these are soot particles, and it's really a historic and a modern era pollutant. It littered the skies when there was dependence on coal in a city like London, before there was access to on-grid electricity and coal-fired power plants moved outside of the city. And we started to catch the pollutants before they were released into the atmosphere, so in the smokestacks. But of course, we've got this coming from rockets as well. And the big difference is that this black carbon is being released into multiple layers in the atmosphere, not just the surface. So all the way from the surface of the Earth to about 80 kilometers overhead. So what's important about these soot particles is that they're dark, and that makes them really effective absorbers of sunlight. And when they absorb sunlight, they warm the local atmosphere. And so we know a lot about black carbon's influence on climate from its production from earthbound sources, but we don't know as much about black carbon's influence from rockets. So these are the pollutants that influence climate. I've mentioned soot, but also water vapor. Water vapor is a powerful greenhouse gas as well. And then there are impacts on stratospheric ozone. So we're releasing these pollutants directly into the stratosphere, located about 15 to 50 kilometers overhead. And so we're putting them right there so that they can contribute to depletion of ozone, whereas our earthbound sources have to spend a lot more effort being transported from the surface of the Earth to the stratosphere before going on to impact ozone. And so the pollutants that I've highlighted here are those that are contributing to ozone depletion. So nitrogen oxides, chlorine, which is well known as an ozone depleting substances, but then also these alumina particles provide a surface for very, very efficient reactions to take place. They behave as a catalyst. Not only are there pollutants being produced from the launch process, but also on this re-entry process. So our main method of disposing of waste that accumulates in space, but also from these returning vehicles and now reusable boosters that, for example, SpaceX uses. They move through this mesospheric layer, producing a lot of energy, very, very high temperatures. And so they're able to convert nitrogen in the atmosphere into this reactive NOx. And once it's in, moves down by gravitational settling from the mesosphere to the stratosphere, can contribute to depletion of ozone. The chemical composition of satellites and rockets also contribute to the production of pollution. So there's a lot of aluminium in these materials, and these can combust to form metal oxides, producing additional catalysts that can deplete ozone. So for comparison, our current natural contributor to NOx in the mesosphere is really meteors. So the estimate is that these contribute about 2 to 40 kilotons of NOx per year. So it provides us with a sort of comparison quantity. How much are we contributing from our artificial sources in comparison to this natural source? And so with our research, what we did is we took emissions from rockets for a single year and put them into a chemical transport model. And in order to do this, we first needed to calculate and map a year of emissions. At the time that we put this together, 2019 was the most recent complete year. And so the focus here is really on 2019. But where I can, I put that into context for 2020, 2021, 2022 because of this substantial ramp up in the number of rockets being launched and the space debris that's building up. And so here is just shown the spatial distribution of these emissions. The size of the circles indicates the number of launches in 2019. So you can see the US shows up as having a lot of launches, but so does China, increasingly India, and then a site in Kazakhstan. But we have a little bit of representation from the Southern Hemisphere as well. The pie charts just show by location the distribution of the different kinds of propellants that are used for the different launch sites or launch countries, sorry. So we've got kerosene, we've got solid rocket motors, we've got hydrogen, and then in some locations we've got hypergolic fuel. It's a particularly hazardous kind of fuel to handle, so many countries have banned its use for rocket launches. So we only see them show up in a few countries. And I should mention that French Guiana is the European Space Agency launch site. So the sort of tropical representation is really coming from European activity in the space sector. Then on the side here, I've just indicated by pollutant type the number of emissions for each. And these numbers don't really have much context on their own, but by comparison, I'll show in a few slides that the amount of soot particles or black carbon that's coming from these rocket launches are 2 to 3 orders of magnitude lower than the emissions that are coming from our earthbound sources. The NOx emissions are separated by launch and by re-entry, just to give an indication of how much this re-entry NOx is. And so it's 2 kilotons. And so just as a reminder, the amount that is coming from meteors ranged from 2 to about 40. So we're on the lower end of the contribution from this natural source. And no doubt with the increase in activity in the space sector, we're going to start to substantially compete with this natural source. So we're seeing a sort of first time increase and overwhelming amount of artificial contribution to pollution in that mesospheric layer. And then I should also mention that in 2019, the number of successful launches add up to 100. And we actually ran the simulation for a decade. And we based our increase over that decade on previous activity. And this represented about increase in 3 launches per year. And we are really being modest in the anticipated growth in the space sector, as hindsight has revealed, because we've reached 135 launches by 2021, so certainly not 3 more relative to 2019, or 6 more relative to 2019, and we're already at 161 in 2022, and there's still more launches planned for the remainder of 2022. So we're seeing this near exponential growth in the number of rocket launches. We're implementing these emissions in a 3D chemical transport model. And so we also, not only do we have to represent them in a horizontal sense, but also in a vertical sense. And to do this, we use information that's already published in the literature that tells us about the vertical distribution of the percent propellant that's burned in each layer in the atmosphere. And so what I'm showing on the right-hand side here is just the vertical distribution of the pollutants that we implement in the model, showing that it's slightly higher for the majority of the pollutants near the surface because of the launch process requiring so much energy. It decreases as we move into the stratosphere and mesosphere, with a slight increase in some of the pollutants higher up. Water vapor is from cryogenic fuel that tends to be used in the latter stages to take the payload to orbit. And then we've got this NOx enhancement associated with re-entering components that range from a mix of discarded items to reusable items, majority from SpaceX and from human exploration. The model that we use only extends to 80 kilometers. It's not going all the way to orbit, but 70 to 90% of the fuel that's burned is actually burned in those lower 80 kilometers. So we're representing the majority of pollution that's coming from these launch processes. And then also, it's important to acknowledge that the lifetime of the pollution in these layers is highly variable. And this is where the implications of rocket launches is really important. The implications are on the environment. In the stratosphere and mesosphere, this region that I've highlighted here, the lifetime of pollutants is greater than 2 years. We've estimated roughly 2.5 years. Other researchers who are looking at this problem as well have estimated slightly higher values. It just ranges depending on the types of models that we're using. And this is because the main loss process is just gravitational settling of these pollutants. Whereas if we're in the troposphere, where most of our earthbound pollution is produced, the lifetime is about weeks to months. And this is because we have rainfall occurring. We have very intense weather systems that essentially wash out the atmosphere. So when rainfall occurs, we see clean skies because all of the pollution has been washed out of the atmosphere. And so what we do is we run this chemical transport model coupled to a radiative transfer model, which allows us to calculate the climate impact of pollutants. And for this, we're particularly interested in the climate impact of soot particles, because as I mentioned, these are dark, very efficient at absorbing sunlight, and so they are very effective at warming the atmosphere. And so the measurement that we use for this is called radiative forcing. And so what this does is measure the change in the energy balance of the atmosphere. So if the values are positive, it means that there's warming. If it's negative, it means that there's cooling. And so the map that I'm showing here is the radiative forcing that we calculate with our coupled model after a decade of emissions, assuming this modest growth in 3 rockets per year. The values range from near 0 to about 2 in the tropics to much, much larger in the poles. This Arctic amplification, for example, shows up in the upper latitudes, and the values can reach up to about 14 milliwatts per meter squared. And then the average across the whole globe is about 4 milliwatts per meter squared. And I'll put that into context in the next slide. But first, just to mention that the majority of the radiative forcing that we're seeing is associated with black carbon or soot. And we can see that in this bar chart separating out different contributors. Polar stratospheric clouds are formed from the additional water vapor that's added from the rocket launch process. But the contribution in sort of counteracting this warming is very small. And so I mentioned I would put this into context. We can compare the effect of rocket launches to the effect of earthbound sources that's been published in the literature already. So the amount that's being produced is 0.5 to 1 kilotons of soot. So the 1 is really by the end of the decade simulation that we do. And we can compare this to the earthbound sources, and there's orders of magnitude different. There's about 6,007 kilotons of soot that's produced based on studies that have estimated these values. And these come from things like ships and gas flaring and diesel vehicles, coal-fired power plants, aircraft. There's a whole range of sources that contribute to that. But then when we think about the climate impact, the rocket soot emissions are only contributing about 0.01% of earthbound emissions, but 3% of the climate effect. And so the implication there is really we don't have to produce the same amount of black carbon from rocket launches as we do from earthbound sources to have a comparable impact or start to make substantial inroads into that climate effect. We've estimated that soot from rockets based on our study is about 400 to 500 times greater radiative effect than black carbon coming from earthbound sources. And the kinds of results that we're obtaining are quite consistent with other studies. In fact, a study came out a week before ours finding similar magnitudes of the effect of these soot particles. There is also depletion of stratospheric ozone, but the effect is quite small. We're seeing that the percent change in the northern hemisphere, for example, is about 0.15% at its peak. And the peak is really very localized. It's in the upper layers of the stratosphere, so about 5 hectopascals or 40 to 50 kilometers. It's in springtime, and it's, as I mentioned, in the northern, in 60 to 90 degrees north. The effect that's happening here is really an equal contribution from that re-entry NOx emissions and from rocket launch chlorine. And chlorine is well known to impact stratospheric ozone. It's regulated for earthbound sources due to that effect through the Montreal Protocol. So I've mentioned this depletion of stratospheric ozone is very local in time and space, but we're finding that this represents about 10% of the upper stratospheric ozone recovery that's been attributed to the Montreal Protocol. So it's really starting to undermine the success that's occurred as a result of the Montreal Protocol. And so the more and more we burn things through the mesosphere, the more we launch chlorine-based rocket fuel, the more we're going to start to undermine the efficacy of that Montreal Protocol. And so I think I'm nearing the end, but just in the last few minutes, I just want to bring back my take-home messages from the research that we've carried out. We're finding that the largest environmental effect of the space sector launches and re-entries is really this climate change associated with soot particles or black carbon. The stratospheric ozone depletion is certainly important, but we're finding that it's relatively small and local. The climate effect of soot particles is large in relation to the emissions that are coming from earthbound sources. So the anticipated growth that we're going to see from the space sector is of particular concern. Our focus was really on rocket launch and re-entry emissions, but there are other concerns that we need to consider too. There's local air and noise pollution, there's supply chain emissions too, and producing the fuel for rocket launches. There's a lot of energy intensive processes that take place. And then, of course, we're cluttering the skies for the astronomers who are wanting to better understand the outer atmosphere, exoplanets, and so on. And then what's really needed is regulation and innovation to help us mitigate the harmful environmental effects of the space sector. And this really requires bringing together a diverse community all the way from the engineers to the policymakers. And so if you want to find out more details about our study, I've just included the link to it. There's no subscription needed. It's publicly available. And then if you want to find out about more research that's underway in my group, I've just included a link to my research group website. And then, of course, if you don't get to ask any questions during the question and answer session and you want to follow up on any aspects related to my talk, I've just included my email here, and I'd be delighted to hear from you. And now I look forward to your questions. Thank you very much for your time and attention.
Fantastic. Thank you very much. That was very, very interesting. Okay, so we've got a couple of questions. If anyone does have any questions, please ask them in the Q&A function. So the first question here is from Tom Reed. Is anyone attempting to use renewables or other alternative power sources to reduce pollution? I appreciate many renewables still produce tailpipe emissions.
Yeah, there are pilot scale studies looking at the use of biofuels instead for rocket launches. And of course, there the issue is that there's probably going to be supply chain concerns associated with this. It really depends on what the source is, what the biomass source is of those biofuels, and whether that leads to the production of more pollutants, perhaps in growing them and harvesting them, in converting land to grow them, and so on. There's also, but I think this isn't even at the pilot stage, it's very exploratory, whether nuclear energy could serve as a replacement, but that I think is even perhaps in the conceptual stage.
Perfect. A question here from Elizabeth. What should companies like SpaceX do to mitigate pollutants and their environmental impact?
Yeah, and this is really the bringing together of engineers, policymakers, and people from these kinds of companies to try and work together to identify viable solutions. SpaceX does unfortunately burn kerosene, which is hazardous to the environment. So that's producing black carbon, water vapor, and NOx. I know that for the Raptor rocket, they are considering liquid methane, which might reduce the overall amount of which would reduce the emission factor, so the amount of pollutant produced per kilogram of fuel, but they're burning a lot more fuel. So that might undermine that kind of progress. And of course, liquid methane, it really depends on whether it's blue or green. What is the supply chain process leading to that liquid methane? And so there might be a shift in emissions from the rocket launch phase to the supply chain phase.
Perfect, thank you. Lindsay is asking, you gave a breakdown of the increase in the number of objects launched. Do you know how much is commercial or how much is linked to the military sector?
Yeah, that is in the report as well. I would say refer to the report. They're all provided for public access, and they break it down in addition to into commercial versus non-commercial. I think within that plot that I showed, there was a bar associated with the military. I think it was the most obscure in that plot. So I'll just head to it. I think it's this SIGINT, which makes absolutely no sense on first look, but if you look into the ESA report, they specify what this is. And so it really contributes a small component. The largest is communication.
Perfect. Carolyn is asking, in your view, do we as a planet actually need so many satellites? Could collaboration minimize this?
Yeah, that's an excellent question. I mean, when we think about SpaceX's Starlink program, for example, and this is all on Wikipedia, and they've probably gathered it from SpaceX's company website. You know, the communication is supposed to be increased internet access for parts of the world that don't have immediate access to internet. And the only real example we've seen from that program is the expansion of internet access in Ukraine. So war-torn infrastructure is damaged. The majority of their access has been to European countries. So yeah, it does seem like there's a bit of redundancy in launching these satellites and providing internet to locations where we already have pretty good access to internet. So yeah, a good question. And I think something that we really need to consider in deciding what to launch into space.
Fantastic, thank you. Emma is asking, please can you explain why there is Arctic amplification, higher temperatures are shown on your radioactive forcing slide?
Yeah, I'm sure the IPCC could do a way better job than me at explaining this. So there's a lot of processes that take place over this location that are contributing to faster warming than other parts of the world. There's feedbacks that are occurring. So we're changing, for example, the albedo, the amount of reflectivity of the surface of the Earth in the Arctic. We're speeding up the rate at which sea ice is melting. And so we're taking away a very white reflective surface and replacing it with a more absorbing dark surface, so the ocean. And that's just one of many processes that are taking place here that's leading to faster warming occurring. And this is a well-known effect as well, just from the general greenhouse gases that we're adding into the atmosphere from our earthbound sources as well.
Fantastic, thank you. Caroline is asking, why are all these emissions unregulated when they negate efforts to solve the climate emergency?
Yeah, this continues to be a discussion, not just by me. Martin Ross is someone who has been in this field for a very long time, who has published a lot of reports and peer-reviewed papers bringing up this discussion many times. We do regulate the space sector. There is regulation associated with deciding the launch site. And in that regulatory process, it's determining whether or not it would contribute to local air pollution, whether there would be leaching of pollutants into the terrestrial environment or the aquatic environment around that launch site. But when it comes to the rocket launch emissions and these re-entry emissions, we really aren't imposing any kind of regulation. And this is really the next step that needs to take place. We need to develop a regulatory framework to prepare for the anticipated growth of the space sector.
Perfect. The final question, any effects of orbiting satellites on nighttime sky brightness?
I don't know if I'm necessarily the best person to answer this. I think the best that I know about this is that astronomers are starting to see a lot more satellites show up in their images as lines moving through it. Yeah, I wonder what would be a good resource to look into that further. Certainly amongst the literature that's being published by astronomers, there must be information on whether or not this is having an effect.
Another question that's actually just come in. Do all objects released eventually burn up?
Not completely. The ideal is that they burn up completely by entering the mesosphere within low Earth orbit. So this is really focused on low Earth orbiting instruments that are at a lower altitude than geostationary instruments that are much higher, and apparently they can just be pushed into the sun. I don't know enough about that orbit to weigh in. But yeah, that's the intended purpose. You know, if they hang around in space, they become a hazard because they bump into other components that are orbiting, other satellites that are orbiting. So the desired end of life for satellites is really burning through the mesosphere. And we have seen examples where that isn't a perfectly efficient process, where rocket bodies are identified in remote locations in Australia, for example.
Fantastic, thank you. Thank you for answering those questions, and thank you so much for the fascinating presentation. That's it from us today, attendees. Thank you for logging in. I hope you found that beneficial and informative.